significantly, not often enough to deduce to make any assumptions on the integrity of the sand body. So, interconnected permeability, we are assuming that the Klinkenberg effect has been taken into account as we are not given any flow pressures. In order for us to perform a Klinkenberg effect correction, we would need two different flow pressures to create a linear interpolation, which is missing. Therefore, we need to assume that it has been applied, and furthermore, a pressure depth correction has been applied. So the permeability and porosity values that we are given have been corrected to the in situ values that the sample would be exposed to. Sonic density and log porosity, as previously mentioned, differs. This is most likely a sign for secondary porosity, such as fractures. The density porosity shows and this is the bulk density porosity, shows the greatest match when it comes to comparing sample porosity and log observed porosity. From this observation, we established a correlation, which was more than significant. The next slide, which is seen here. Permeability and porosity for the core samples show coefficients of variation, R-squared values, and regression coefficients that are more than significant, indicating that there is a strong trend. There is one outlier, which is the bottom right, which is X4, and maybe from the pictures, I'm not sure if it comes across, X4 has the lowest sample size. Therefore, we assume that the sufficiency to adequately represent the population has not been met, and the correlation coefficient does not go in line with the other three wells. We're considering it an outlier. Based on the other three, we have established the correlation in the form of a formula of a function, and we have applied this, next slide, to the bulk density log data that we have. This allowed us to create synthetic permeability logs. Well, synthetic, I say synthetic because they're not from any logging tool directly. They are deduced from the bulk density. And this is a integral part of our later model construction. But more on that on reservoir simulation. Next slide.
Yeah, it's over there.
That's over there. So, sand and shale differentiation. The main difficulty between sand and shale differentiation arose from the inaccuracy related with the gamma ray log. As it can be seen for X1, the volume of shale calculated from the gamma ray log shows a very consistent high content of shale, which contradicts the neutron density cross plot, which clearly identifies a clean sand, where the gamma ray shows a radioactive sand. Therefore, the volume of shale calculations were based entirely on the neutron density, as we assumed the gamma ray to not be reliable enough to accurately predict the shale contents of the formation. The reason for that could be, one of the reasons for that could be that X1 was the first well drilled and was named Wildcat Well. We are assuming that during that exploration drilling, the uncertainty about the pore pressures that will be encountered was very high, so the mud applied was very heavy, and heavy mud is mostly, especially back in the days when this well was drilled, it was 1977, I believe, barite was the main additive in mud to increase the density and hence the weight. So we are assuming that that these wells have been contaminated, or the sand has been contaminated by radioactive particles from a heavy mud, rendering the gamma ray analysis unreliable. Next slide. Time. The water saturation was estimated using the Archie's equation. The cementation, all of the necessary exponents were provided from fluid analysis and available data. We have formation factor versus pressure data given for some of the wells, not all of them. Whenever it was not available, we resorted to the Humboldt equation and assumed the standard inputs for the necessary parameters. The RW value, which was obtained from the Pickett plot, and in turn we were able to estimate levels of oil saturation in the red the red log shows the oil saturation, and this in turn helped us to define our whoops. Let me go back.
Yeah.
There you go. This in turn helped us to define our net to gross ratio. Now, the net to gross ratio is essential in estimating STOIP, and the main zone of interest is obviously the pay zone. Now, the criteria by which we define the pay zone is lithology or rock that can store hydrocarbon and that can flow hydrocarbon. Now, in order to store hydrocarbon, the porosity must be met, the porosity criteria must be met, and in order to flow hydrocarbon, the permeability criteria must be met. And obviously the water saturation is an integral, an essential variable in the determination of this. This is a screenshot from TechLog, which is the main software we used in log analysis, and we used, because of lack of experience, we used the preset cutoff criteria for porosity. I believe it's 20% or less, to determine pay zones and reservoir zones, pay zones, and what's the other one? Doesn't matter. Next slide. Oops.
Yep, done.
Okay. So oil-water contacts differed throughout the reservoir. From repeat formation testing, we have reliable information on the oil-water contacts for 4 wells. 2 wells located in the northeastern sector of the reservoir, namely X5 and X6, highlighted in blue, have a lower, shallower oil-water contact than the remaining wells. The assumption how that could arise, a lot of discussion led us to the assumption, or to the conclusion, that only 3 possibilities could be the reason for the difference in oil-water contacts. The least likely, from our remaining analysis, the least likely scenario is compartmentalization. We don't have enough evidence to definitively say that the reservoir is compartmentalized. So, but it is one reason for differing oil-water contacts. However, not the most likely. The second, less likely, but in the intermediate range of probabilities, is a hydrodynamic aquifer, a flowing aquifer, shifting the oil-water contact upwards in certain sectors and causing it to slump in others. And the most likely scenario, which we are going with, is a trapped water contact, which is, next slide. Okay, I missed the slide. These are the RFT data that were available, or this is the RFT data available from the folders that were provided. Next slide. This is the scenario of trapped water, indicating how a possible difference in oil-water contact could be explained. However, there's not enough information to definitively comment on this scenario, on the likelihood of this scenario. Next slide. Lawrence plots show a degree of variance throughout the formation. They indicate the heterogeneity of the sand body. The semi-variogram shows a repeat or a repeating trend, showing or indicating sedimentation laminae repeating itself throughout the reservoir with depth. Next slide. We attempted at estimating the expected subsidence of the platform, since it is unconsolidated or not well consolidated sand. The subsidence was estimated using the average fractional pore volume change, which was made available from core data, multiplying the from simulation obtained pressure drop in the reservoir with the average fractional change. We estimated there's an error in this slide, it's not days, it's years. We estimate the and this is a linear estimate, it's the actual estimate is far more complex, a linear estimate of around, at the peak, 8 feet of subsidence. So subsidence is an issue that the field or the platform might encounter, given that this is something that's happened in the North Sea before. Next slide. Oh, that's it. All right.
Good afternoon again. My name is Mohammed Osman and I'll be presenting you reservoir engineering part of the FDP project. We divided into 3 different analysis stages: PVD analysis, scan, and well test. Purpose of PVD was to understand the reservoir fluid present we had. We had data available from 4 different wells: X2, 3, 5, and 6. No data from well X1 and X4. So we are assuming whatever the oil, the concentration of oil found here is going to be constant throughout the reservoir itself. The oil gravity, it's 40.9 API, indicating light oil. Reservoir pressure is 5,700, bubble point at 1800, so it's an unsaturated reservoir. The reservoir temperature is 263 degrees Fahrenheit. The histogram below shows you the concentration of different carbon molecules present. You'll see the majority is actually with light carbon molecules, C1, C2, C3, and some concentration of nitrogen and carbon dioxide. PVD data does not show any presence of H2S at all, but production data, the only production data that we have from well X2 shows a very minimum concentration of 2 to 5 ppm. That was actually during the initial stages of product testing that they had. Other than that, depending on these H2S production data and presence of carbon and nitrogen, we've selected our tubing and wellhead materials, which will be later discussed in the drilling section. This is a continuation of an explanation that Lorenzo gave us in the previous slides. Special code analysis. The 4 major code analysis present with us was from well X1, X2, X4, and X5. X1, X4, and X5 was actually provided with us correlated with depth. We had air permeability, porosities, and grain density. Whereas X2, we only had a plot between porosity and permeability provided with us, which we tried to mimic, which we also tried to mimic so that we can show you a better correlation. Again, I'll just repeat it and I'll give you a small summary of what Lorenzo told you before. We have a maximum correlation between X1 and X5, whereas X4 has the least of them. And you can see the number of samples provided was around 128. Our main assumption is if we had further more samples at more depths, we might have gotten a better correlation between them. Since we've already have a good correlation match between porosity and permeability with these, we move on to make a correlation between porosity versus density. Again, if you look at porosity versus density, gives you a very good correlation. It's about 81%. As the porosity decreases, we have an increase. As the density decreases, you see an increase in porosity. Same can be said for density versus permeability. Again, an R-square value of 71.9, 72%. Now, using these, we actually made the permeability against depth correlation, where the red actually is blue is the estimated permeability values and red is the observed. You can see they're perfectly overlined over each other. And as you see, as the depth decreases, the permeability keeps on decreasing. Moving on to well test analysis. Again, I'd like to first point out the amount. We had actually 4 appraisal wells giving us well test analysis. This is a summary of the data already available through the well test. Was the formation thickness, productivity index, skin values, and the actual PI values, which are later on calculated. One anomaly which was seen in these wells were very high skins that we encountered. Again, what we believe is, and was also spoken to you by Lorenzo also in the previous slides, we believe this is due to the presence of very heavy mud being used during the drilling of these appraisal wells. That's why we encountered these high skin values. Whereas the pay zone thickness differs, where X2 and X6 shows the exact same pay zone thickness that was deduced by the log analysis, whereas for other wells they are pretty high. That means well test analysis were actually carried out in a much larger, thicker zone. Like it wasn't confined to the pay zone itself, but it was carried out further out too. We have a constant single phase fluid throughout. We've assumed a single phase fluid and a constant low compressibility throughout the well test analysis being carried out. If you look at the first one is the X2, we had in total of 8 rate changes, out of which the final drawdown and build-up was the longest